Here we start the syllabus of the module functions of the complex variables. And first of all, we discuss the Cauchy Riemann conditions. The Cauchy Riemann conditions discuss the differentiability of a complex function. So, differentiability means whether the derivative of the function exists or not. So, we already know how to define the derivative of a real function. So, suppose f of x is a real function, the derivative of the real function is defined as limit delta x tends to 0, f of x plus delta x minus f of x divided by x plus delta x minus x. So this is nothing but a limit delta x tends to 0, delta of f of x, a small change in f of x divided by delta x, and which is defined as the derivative of f with respect to x. This is df by dx, or it is also called f dash of x. So analogous to this, the derivative of a complex function f of z is defined as limit delta z tends to 0. So instead of the real variable x here, we can have the complex variable z over here. So limit delta z tends to 0, f of z plus delta z minus f of z divided by z plus delta z minus z. So this is nothing but limit delta z tends to 0, delta of f of z, a small change in the complex function f of z divided by delta z. And therefore it is defined as the derivative of f with respect to z, df by dz, and which is also called f dash of z. So we already know that for a real function, in order that the derivative to exist, the function should be continuous on the real axis. So the real function is defined on the real axis, and for the function to be differentiable, or the function should be continuous on the real axis. That means suppose we have a point like this, then in order for that the derivative to exist at this point, then the right hand limit is equal to the left hand limit at this point. Okay, so at this point, f of x from x is equal to 0 plus z equal to f of x at x is equal to 0 minus. So the limit should be equal. Suppose the point is 0. So while approaching this point, the right hand limit and left hand limits are equal. So now, but we know that for a complex function, it is defined on the plane. It is a two-dimensional plane. So for complex functions, we have a two-dimensional complex plane, and a complex a point here is represented as a point on the plane. So here we can have different directions of approach to this point in the two-dimensional plane. In this real axis, we can have only two directions of approach, but here in the complex plane, there are different numbers possible directions of approach for the complex function. So, for the complex function to be differentiable, the limit should be independent of the direction of approach. So that is the condition for differentiability or the existence of derivative for a complex function. So we can define a complex function f of z here. So the complex function here is given by f of z is equal to u plus iv. U forms the real part of the complex function and v forms the imaginary part of the complex function, and z here, which is the complex variable, is nothing but x plus iy. Okay, now so here the point z is the ordered pair x comma y. So the increment in z depends on the increment of x and increment of y. Okay, so when x and y changes, z changes. So the increment in z delta z is equal to delta x plus I delta y. Delta x is the increment in x and delta y is the increment in y. And here delta f is equal to f is u plus iv, and therefore delta f is delta u plus I delta v. Now we can find delta f by delta z, which is equal to delta u plus I delta v divided by delta x plus I delta y. So now f dash of z, the derivative of this complex function, is defined as f dash of z is equal to limit delta z tends to 0 delta f by delta z. So we have to find this quantity and we have to apply the limit delta z tends to 0, then we get the derivative of the function. And we have seen that this derivative should be independent of the direction of approach. So we have seen that there are different possibilities for the direction of approach, and here we consider two cases. So the first one is that suppose we are approaching the point z along the horizontal line parallel to x-axis. So this is case 1. And the second case is that we are approaching along the vertical direction parallel to y-axis. So we are discussing these two cases only. So case number 1 is we are approaching the point z along the horizontal line parallel to x-axis. So along this line, and we know that for this line y is a constant, and therefore delta y equal to 0. Y is a constant for the line which is parallel to x-axis, and therefore delta y equal to 0. And we know that delta z, which is equal to delta x plus I delta y, is equal to delta x alone, since delta y equal to 0. Delta z tends to 0 implies delta x tends to 0, since delta z is equal to delta x. So the derivative here, which is f dash of z, can be represented as limit delta z tends to 0 delta f by delta z. So instead of delta z, we can write limit delta x tends to 0. So here f is u plus iv. So delta f is delta u plus I delta v. And we have seen that delta z here is delta x alone, since delta y is 0. So in the denominator we have delta x alone. Okay, so we can write this as two terms, and therefore we limit delta x tends to 0 delta u by delta x, and I can be taken out of the limit. So I multiplied by limit delta x tends to 0 delta v by delta x, and we already know that this first term is nothing but the partial derivative of the function u with respect to x. So that is dou u by dou x, plus the second term is I multiplied by. So this term is nothing but dou v by dou x. So since v and u are functions of both x and y, so this defines the partial derivative. So these are multivariable functions, and therefore this quantities gives the partial derivative. So let this be the equation number 1, f dash of z when the point is being approached along the horizontal line parallel to x-axis. So this equation is true assuming the partial derivative exists. So now we can have the case 2 where we are approaching the point z along the vertical direction parallel to y-axis, and we have seen that in this case x is a constant and therefore delta x is equal to 0 here. So in this case delta y was 0, but here delta x is equal to 0. Okay. And delta z, which is delta x plus I delta y, is I into delta y alone, and delta z tends to 0 implies I into delta y is 0. So since I is not 0, it is delta y tends to 0. So delta z tends to 0 implies delta y tends to 0. Okay, f dash of z here is limit. Instead of delta z, we can write delta y tends to 0. Delta u plus I delta v divided by, and delta z is I delta y. So this is limit delta y tends to 0. So 1 over I is minus I into delta u plus I delta v divided by delta y. This can be written as two terms. First term is this, and second term is limit delta y tends to 0. I square is minus 1 and there is a minus over here. So that is plus 1. Delta v by delta y. And we know that the first term taking minus I outside is nothing but dou u by dou y. And the second term is dou v by dou y. So this is the derivative of the function when we are approaching the point along the vertical direction, and this is termed as equation number 2. And for the function to be differentiable, the derivative should be independent of the direction of approach, and therefore equation number 1 and 2 should be identical so that the function is derivable, or to have the derivative for the function. So by equating equations number 1 and 2, we get dou u by dou x plus I into dou v by dou x is equal to minus I dou u by dou y plus dou v by dou y. So since the left and right sides are equal, their real and imaginary parts are separately equal. So equating the real part, we get dou u by dou x is equal to dou v by dou y. And by equating the imaginary parts of this equation, we get dou v by dou x is equal to minus dou u by dou y. Or we can write dou u by dou y as minus of dou v by dou x. And these two conditions are called the famous Cauchy Riemann conditions. So these conditions predict the differentiability of a complex function, whether the derivative of the function exists or not. So these equations, dou u by dou x equal to dou v by dou y and dou v by dou x is minus dou u by dou y, are the Cauchy Riemann conditions or CR conditions, and they predict the existence of the derivative of the function. So if the function is differentiable, the Cauchy Riemann conditions are to be satisfied. So if df by dz exists or the derivative exists, the Cauchy Riemann conditions must be satisfied. So the Cauchy Riemann conditions read: the partial derivative of the real part of the function with respect to x is equal to the partial derivative of the imaginary part of the function with respect to y, and the partial derivative of imaginary part of the function with respect to x is equal to the negative of the partial derivative of the real part of the function with respect to y. So these are the famous Cauchy Riemann condition. So if a function is differentiable, that function is also called an analytic function. So for a function to be analytic, the Cauchy Riemann conditions are satisfied. or if the Cauchy Riemann conditions are satisfied, the function is analytic. Okay, thank you.